Hi folks, this is Calc 1, Checkpoint Quiz 14. We're asked to find the area beneath a curve between two different x values. Alright, so let's sketch out the problem situation. We're given the curve y equals 4 minus x squared. So we know from algebra, or even from calculus if we wanted to go that route, that that's a parabola with a vertex at 0, 4. It opens downwards. And it's got a pair of x-intercepts at -2, 0, and at 2, 0. So we're going from x equals -1 to x equals 2. So x equals -1 would be right here. X equals 2 would be right here. And so we're looking for this area. Okay, the function here that's involved, f of x equals 4 minus x squared, is a continuous function. It's a polynomial. And so we know from our theorem in class that we can get this area using the limit process. We can use right-hand sums, left-hand sums, midpoint sums, or anything in between there. And so for us, we're going to use the right-hand sum. And so we've developed the right-hand sum formula for a generic function on a generic interval AB. And it's equal to b minus a over n times the summation, I goes from 1 to n, f of a plus I times b minus a over n. So once again, the b minus a over n is the width of each of the rectangles we'd be chopping up. The a plus I b minus a over n is the formula for the right endpoint for each of the subintervals. Okay, so let's plug in b is 2, a is 1. So this is 2 minus -1 over n times the summation, I goes from 1 to n, f of -1 plus I times 2 minus -1 over n. So this is 3 over n times the summation, I goes from 1 to n, f of -1 plus 3i over n, which is 3 over n times the summation, I goes from 1 to n. I'm now going to substitute this into my formula, and that's going to be 4 minus the quantity, -1 plus 3i over n, quantity squared. And now the object is to simplify this, break the summations up, and use the formulas we have from the book about summing from I goes to 1 to n of various powers of I. Okay, so we start to simplify. I've got 3 over n summation, I goes from 1 to n, of 4 minus, and I'm going to square this out. So -1 squared is a positive 1, minus 3i over n, minus another 3i over n, gives us minus 6i over n, plus 9i squared over n squared. So this is 3 over n, summation, I goes from 1 to n. 4 minus 1 is 3. This becomes positive 6i over n minus 9i squared over n squared. Now I'm going to use properties of sums. I'm going to use the associative and commutative property of sums. I'm going to get 3 over n times the summation, I goes from 1 to n, of 3, plus the summation, I goes from 1 to n, of 6i over n, minus the summation, I goes from 1 to n, 9i squared over n squared. So continuing here, we have 3 over n times. We can evaluate this sum because this sum means we're adding 3 to itself n times. So that's 3n plus. For these last two sums, I'm going to factor out everything except the i's. So it's going to be a 6 over n times the sum I equals 1 to n of I minus 9 over n squared times the summation I goes from 1 to n of I squared. So I get 3 over n times 3n plus 6 over n times the sum from I goes from 1 to n of I, that's n times n plus 1 over 2, minus 9 over n squared. The sum I goes from 1 to n I squared, n times n plus 1 times 2n plus 1, all divided by 6. So once again, these are two formulas you're going to need to know from the book. Now I'm going to distribute my 3 over n to each of these terms and simplify. So I multiply 3 over n times 3n. The 3's multiply to give me 9. The n's cancel. So I get a 9 there. When I multiply the 3 over n to the second term, I'm going to get cancellation within the second term. That's going to cancel out. So I get the 3 times the 3, which gives me 9, times the n plus 1 there in the numerator. And in the denominator, I'm going to pick up an n again. On the third term, once again, before I multiply, I can do a little bit of simplification here. I get the 3 times the 3 gives me the 9. I get the 9 back, and that's going to be n plus 1 times 2n plus 1. And in the denominator, I have the 2n from before, but now I pick up another factor of n to give me 2n squared. So once again, remember, what does this expression represent? If I take that parabola from -1 to 2, and I chop up the interval from -1 to 2 into n equal pieces, and if on each of those pieces I'm using the right endpoint to draw my rectangles, then the total area of these rectangles is given by this expression. So to find the actual area, we're going to take a limit as n goes to infinity. Okay, so as we mentioned before, since we have a continuous function on the closed bounded interval, the area is going to be the limit as n goes to infinity of the area of the value of the right endpoint sum. And this is what we got for the right endpoint sum. So we take a limit as n goes to infinity, and we apply what we know from limits at infinity. So the 9 is not really going anywhere. But we factor out the highest power in the numerator, which would be an n. And if we factor an n out, remember it's the same as dividing by n for that quantity. I can factor an n out of the first quantity and an n out of the second quantity. So I have a 9n squared, 1 plus 1 over n, times 2 plus 1 over n, over 2n squared. And I see that the highest power of n's cancel in these terms. And as n goes off to infinity, that's just going to go to 9. This quantity, well, the 1 over n goes to 0. This quantity goes to 1. I get 9 times 1 minus. And 1 over n goes to 0, so this goes to 1. This goes to 2. So I have 9 times 1 times 2 over 2. And so what do I get for my final answer? I get 9 plus 9 minus 9 for a grand total of 9. So that means the area is 9 square units, whatever the units were. That'll do it for quiz 14.